So for the part 1, which is Kirchhoff's first law, so we look at which junction we look at here. So can you see the current entering is I1 and I2, current leaving is I3 lah, so it's I1 plus I2 equals to I3. So for the next one, if you are talking about X, B, C, Y, X, that means you're moving from X to B to C to Y to X. That means we are traveling anti-clockwise. So how do you read the loop when it's anti-clockwise? We do the EMF first. So we look at this EMF. So by the way, we label all the direction of EMF first. And direction of EMF is the direction that the cell wants to push current out. But whether or not the current really goes here or here, it doesn't matter. Direction of EMF, just look at the polarity of the cell. If this is negative, this is positive, current is supposed to flow this way, so we label direction of EMF. Now, if let's say this cell E1 is used to charge E2, current will flow from here to here, right now. But you still wouldn't change the direction of the EMF. Direction of EMF still remains the same. It's the direction that it wants to push a current. Whether or not it pushes that way, it doesn't matter. Okay? So when we move this way, X, B, C, Y, X, direction of travel is this way, from Y to X, and the EMF also same direction, so it's positive EMF. So you write as positive E2. But there are two resistors here, so equals to, so let's do the PD. So direction of travel is this way, from X to B to C to Y to X. So it means from B to C is moving to the right. Current through this resistor, which is I3, is also to the right. So if it's to the right, that means same direction, current through the resistor and the travel, so it's positive PD. And PD is given by what formula? Unity. What's the formula for PD? V equals to IR. So we take the current I3 times R3. Understand? So you get positive I3 R3. What about from here? We come to this side. So the PD across this R2 is also IR. The current is this way from Y to X, which is I2. The what do you call it? The travel also same direction. So it's positive or negative PD, Brendan? Positive or negative PD? You read. So Brendan, positive or negative? Positive, very good. So what is the formula for PD? IR. So what is the I? What's the resistance? So it's I2, R2. Understand that? So the final one, AXYDA, AXYDA. So if you're moving this way, direction of travel is from here. So that means same direction as EMF, so it's positive E1. But if I come down here from X to Y, direction of travel and direction of EMF is opposite, so it's minus E2. Then what about the PD? If I'm moving from here to here, which is this way, my current through R2 is opposite. Can you see that? So therefore it's negative I2 R2. But when I come to here, my current is same direction as travel, so it's positive I1 R1. Okay? So for the part 1, Wee Kiong, did you get the answer here, this one? So the I1 is entering, and what else is entering? And what is leaving? What is leaving? What current is leaving? So I1 plus I2 entering equals to I3 leaving lah. Okay, very good. Alright, next one for the second one, BCXYB. BCXYB. So when you do from B to C to X to Y to B, which is moving anti-clockwise, so when we pass through this cell, is our travel opposite or same direction as the EMF, Abigail? This part, travel and EMF, same or opposite? So it should be positive or negative? So negative E2 lah, right? So the answer is negative E2. Now then we will travel through these two resistors. So this resistor, we are traveling, remember, this way. So that means we are traveling from C to X, but your current is same or opposite, Abigail? Direction of travel and current, same or opposite? So your current and the travel, same or opposite? So your PD is positive or negative? So what is the formula for PD? For PD of this? what are you using here? So how Abigail's answer? Positive or negative? Negative I2R. What about this part? What is the PD across this top R? Positive or negative? Negative. Because direction of current is to the right, but travel is to the left. Okay. So if you move from A, the next one, A, B, C, X, Y, Z, A. That means A, B, C, X, Y, Z, A. So we travel this loop. There are two cells here. So this cell, as I'm traveling this way, same direction or opposite direction to the EMF. Brandon. Same. So what's the answer? Positive E1 or negative E1? Positive E1. Now when you come down here, you're traveling to the right, but the EMF is to the left, so the EMF is positive or negative? So it's negative E2, correct? Now then there are how many resistors? 1, 2, 3 resistors. So as I'm traveling this way, let's talk about the current here. So I'm coming down. Current I1 is also down, right? So what is the PD across this? Positive what? Positive I1R. Okay, very good. So then in the end, you get E1 minus E2, positive I1R. Now when you come to here, we are coming to the right, but the current is I2 to the left. So it's positive or negative PD? So it will be negative I2R. Then we come to this resistor, we are going up. Current is what? Now, some people get confused about the current here. They thought the current is I3 or I2. Now, how to determine the current is you must look at a series circuit when there's no branches. That means there's no way the current will split. For example, if you take this current, there's a branch here. If you take this current, there are branches here. So you cannot take the current here and here. But you can take the current I1 because you notice it's connected to here without any branches, without any splitting. So you can be sure that this is I1, this has to be I1. That's why I will draw the I1 this side. So here the travel is this way, current is this way, so it's positive or negative PD? So answer is, what's the PD here? Positive I1R. Very good. So for the first part, for Kirchhoff's first law, if we were to take the current entering and current leaving, so let's say we take current at B here. So what are the currents entering, Ziyun? I1 and what is the current leaving? So I1 plus I3 goes to I2. Very good. Now for the second loop, which is H, B, J, F, G, H. So remember, as you're traveling here, the current in BJ is not the same as the current in JF. Why? Because can you see that here, when the current is passing, I2 is passing through BJ, there's a junction when there's two branches. So the current may not be the same. So what is the current here? The best way is to trace back in series where does the current come from. So if you look at this whole thing is one line with no branches. So since this is I1, that means the current here is I1. Current is flowing here I1 right now. That means current must be coming here I1 as well. So remember, current here is I1, current is I2. Now they did tell me that the total resistance of the wire is R2. So this is R2. Since BJ is halfway, they told me BJ is halfway. Connection at J is halfway. So the resistance of this will be half, which is how much? Will be R2 over 2. And this will be R2 over 2. Okay. So let's do HBJFGH. Okay. So let's do this loop. So what is your answer? Zian again. So when we're traveling from here, this loop here, when I'm traveling to the left, my EMF is to the left or right? So it's positive or negative EMF? So it's positive E1. Okay. Then when we come to here, there's no more cell already, so there's only one EMF. So let's look at PD now. So for PD, let's talk about this PD here. Is my travel the same as current? Yes. So what's the PD? Times? Yes, very good. I2 times R2 over 2. What about for this side? What's the PD? Yes, very good. I1 times R2 over 2. And finally, this PD? Yes. And what about here? Yes, very good. Because all of them are in the same direction, current and travel. Okay, now, so all positive. So the next one, which is H, B, C, J, F, G, H, so which is this big loop here. So there are how many cells here? Okay. Two. So the top one, my direction of travel and EMF same or not? So what's the EMF? And for all about the bottom one? Yes, because my travel is opposite to EMF. So it's E1 minus E2. Then when we do PD, okay, let's start off with this resistance first. So if I'm moving this way, my current also this way, so it's positive or negative? So what's the PD? I1 R1. What about for this? Okay, very good. What about for this one? Negative I3 R2, because I'm traveling this way, but my current I3 is this way. How do I know my current is here? Because I'm tracing from here. So can you see the I3 moving here? So I3 is here. So my travel and current is opposite. So it's negative I3 R2. And finally for this, I'm traveling same as current. So what's my PD? I1 times R2 over 2. Okay, that's how you use Kirchhoff's second law. Now for this question, you have actually two cells, but do you notice that this 4.4 volts and 2.1 volts, which is bigger? Catherine, which is bigger? So how will current flow from 4.4 to 2.1 or 2.1 to 4.4? 4.4 to 2.1, correct, because it's charging. Understand that? It always flows from higher to lower EMF. Okay, very good. Now, when you want to use Kirchhoff's second law to find the current, so let's assume the current is flowing here, which is what we are doing is answering the next part already lah. But we are answering this part before you're answering this part. So in this loop, okay, so if you want to label, you can label A, B, C, D. Then we can do this direction A, B, C, D, A. So let's do loop A, B, C, D, A. Now it's not compulsory to go clockwise. You can go anti-clockwise. But if you want to have fewer negative terms coming out, it's easier to do in the direction of current, but it's not compulsory. So if I move this way, my direction of travel and my direction of EMF, 4.4 volts is same or opposite? Huh? Same. So it's positive 4.4. What about from here? I'm going here, but my EMF is this way, right? So it's positive or negative? So it's minus 2.1. Now, what about for PD? PD is easy because all the currents are in the same direction here, and we are also traveling the same direction. So all the PD will be positive or negative? Positive. So therefore, the PD here will be I times 1.8, I times 5.5, I times 2.3, which is all here lah. So you group together the I, factorize it, and you should be able to get your current as 0.24 amperes. So next one, we already done the current. So part 4 here, calculate the PD across resistor R. So what's the PD here? So PD is quite straightforward. V equals to IR. So we know the current, which is 0.24 amperes. We know the resistance, so you just multiply and you will get your PD. So next one, you'll talk about terminal PD across cell A, and then terminal PD across cell B. To find terminal PD across cell A, you must understand how the current behaves. Because 4.4 volts is used to charge the 2.1, so the current is flowing this way. So which means to say, when the current is coming along this direction, as it passes through this internal resistance, it will lose or gain energy. It will lose, right now. So the potential will drop. So the potential will drop by how much? IR. So the PD is IR. And when it comes to 4.4 here, it gains or loses energy. Gains. So here the potential will increase. So it loses IR, then it gains 4.4. So that means if we measure across here, you will take 4.4 minus IR. Maybe I use a different way to explain to you. Okay. Now, for example, let me just move it a smaller bit. If we were to consider the potential here is 0 because just before the cell is 0. There's a PD of 0.552. If you take current times this resistance, you'll get 0.552 volts. That means the difference here is 0.552. So this is 0. This potential is 0.552. So let's say from here it drops to 0, but here it gains again 4.4. So when the voltmeter is connected to find the PD, terminal PD, you'll connect from here to here. So one side is 4.4, one side is 0.552, so you end up minusing them. Understand not? That's why you end up minusing. But when you come to here, it's something different. Next part, terminal PD across cell B. When you go terminal PD across cell B, now don't forget your A is charging your, means the cell here on top is charging the cell at the bottom. So when the current passes through this cell, it loses or gains energy. It loses. So it loses 2.1 volts here, and then it loses another IR here. So therefore, the terminal PD you must add up. So it's 2.1 plus IR, because this is a loss and a loss. Whereas the top was different, it was a gain, it was a loss and then a gain. You see the difference? But for this is both losses. For example, if let's say this is 4.4 volts here, so the whole line here is 4.4 because there's no resistance in between. Now it transfers 2.1 volts to this cell because it's charging this cell. So after transferring 2.1 volts, it drops to 2.3 volts. From 2.3 volts, it has a PD of 1.8 ohm times 0.24, so it will drop again. So finally, if you measure from here to here, it is 4.4 minus 1.87, which is 2.1 plus IR. So this is the terminal PD across cell B. So very important now, this one you add, this one you minus, but this one you add. Why? Here because part of it gain, lose, part of it gain. Here both also lost.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.